Oscar Peverini from the National Council of Italy, and in this presentation I will discuss on recent developments in the application of the selective laser melting technology to the manufacturing of all metal microwave components. Melting is one of the power bed fusion processes. Power bed fusion process, a thermal energy source is used to selectively fuse regions of a powder bed. Depending on the thermal energy source that is used, the processes can be defined. The most common ones are selective laser sintering and selective laser melting, where laser is used to bind the powder bed. Another one is electron beam melting, where instead an electron beam is used. In the laser melting process, the part is built over a building platform, where a coater spreads a layer of powder. Then laser is used to consolidate the traces of interest in that layer. Then, when the layer has been processed, the building platform is lowered, and a coater will spread a new layer of powder. All these steps are repeated until the complete part has been built. A SLM system is characterized by several parameters. Some of them are reported in this table. The relevant from an RF point of view are the effective building volume, that is typically around 25 centimeters times 25 centimeters times 21 centimeters, and this somehow define the maximum part that can be built. Another parameter is the layer thickness, and depends on the material that is used. Typically, values ranges from 20 to 60 microns. Yttrium laser is used with some hundreds of watts that actually can melt the powders. And then finally, the diameter of the beam laser is typically 0.1, 0.2 meters, and defines the actual resolution and accuracy of the system. The melting process is made of some basic steps. First one is the conversion from CAD model to a lithography STL format. In that, 3 tasks are carried out. The first one is slicing. In selective laser melting, as in all the additive manufacturing processes, part is built by the material layer by layer along the direction that in this case is the vertical direction. We will have a discretization of the CAD model along the vertical direction, and this gives rise to the well-known staircase effect. The task is the design of the supporting structures that are needed to support all hanging surfaces. All these surfaces are surfaces for which, in the previous layers, there is no powder that has been consolidated. And if no supporting structures are used, these surfaces can deformate or even collapse. In other, supporting structures are also inserted in order to minimize heat conductance, in order to minimize thermal stresses during the process. The task is the optimization of the part orientation in the built-in platform, and is strictly connected to the design of supporting structures. And just to have an example, if you are considering to develop a waveguide filter made of just a single metal block, then not have any access to external channels. So you cannot design and even build supporting structure for surfaces of the internal channels, and because otherwise you will not be able to remove after the building process. In order to avoid these surfaces to collapse, you orientate the part properly over the building platform. The basic step is the building process itself. It is characterized by several parameters that can vary the quality of the final part that is built. Two of them are the beam offset correction, the beam correction that takes into account the enlargement of the laser beam due to thermal conductivity, conductivity, and the action distance between two adjacent traces that are affected by the laser. The values of these parameters, you vary the quality of the final part, like accuracy, roughness, and density. And we will end up with the parts attached to the building platform through the supporting structures that are visible here in darker gray. The parts that have been built, we attached them from the platform. But before doing that, the platform and the parts go a stress relieving process that depends on the metal that has been used. In aluminum parts, the stress relieving post-processing occurs in air for 2 hours at 300 degrees Celsius, that is normal oven. But considering titanium, this process occurs in high vacuum in order to avoid dangerous reaction between air and titanium that occurs at very high temperature, around 700 degrees Celsius. The part has been undergone stress relieving. It can be detached and is cleaned from the part that has not been processed. Then the parts undergo a shock cleaning post-processing in order to improve the surface quality. You can compare the surface quality of a part before and after of the shock cleaning post-processing. And by introducing the part in flux of glass microspheres at some pressure around 8 bars, the surface roughness can be decreased by roughly 45 to 50 microns down to 5 microns. This is about the process itself. What is the radio frequency application of this technology? In the table, we can read some of the works that have been published recently with the material, the coating, the devices, and the band. As a summary, we can say that most of the works deal with aluminum as a material. Coating was necessary. Where components have been developed. Additive bands are X and Q bands, that is from 10 to 20 gigahertz. Since aluminum is the material most used in these applications, let's see what kind of alloy is used. They are made of aluminum, silicon, and magnesium. It is widely used in aerospace and automotive industries because of very good properties in terms of strength, resistance, thermal conductivity, electrical conductivity, that around 5-10 megasiemens per meter. The final density can be as high as 99%. The process is quite reliable. We mention accuracy around 50 microns, depending on part size, on the powder, or on the process parameters. The roughness is between 4 and 40 microns, and obviously it depends on the properties of the shock cleaning. The size of the particles is between 5 and 50 microns, and the minimum feature size, the feature resolution, is around 0.5 millimeters. Now, let's see some more in detail some examples out of the list I shown before. The first one comes from the National University of Singapore that has developed this feedback patch antenna array. The nice feature of this array is that the 4 patches are funded over ground plane without using any dielectric substrate. By that, these researchers have avoided the additional losses due to the dielectric and have achieved very high performance in terms of efficiency, that is around 0.9. Another nice feature is that the structure can be perforated, and this gives rise to a very lightweight structure. The concept has been applied by the same group to an X-band feed ore. Say that the perforation of the structure is performed in a different way in vertical and in the horizontal walls. In vertical holes, we have some transversal vertical cuts because the currents that are shown in green arrows are transversal, where in the horizontal hole, the currents are both longitudinal, that is the red arrows, and transversal, so the vertical ones. So in this case, the perforation has to be done by using square grids. And also in this case, the researchers end up with very good results in terms of radiation pattern, in terms of gain and polarization. The last for the same group demonstrates the capability of the selective laser technology of integrating functionalities. In this case, this group has developed a slot array that is shown here with integrated monopulse comparator in just one single metal piece. And at the end, they achieved a very lightweight assembly with a height of around 600 grams. They created the capability of integrating innovation of functionality through SLM. They achieved also quite good results in terms of the radiation patterns, both for the SAM mode and the delta mode, both for the azimuthal and elevation angle. And comes from Earth's different space. In this case, the researchers have the free-form capability of the selective laser melting technology in order to develop Ku band filters with very high Q factors and to reduce the impact of the surface roughness on the insertion loss using ellipsoid cavities that are shown here. They developed a single block component that has been space qualified. Last examples come from the National Cancer Research of Italy and the Institute of Technology of Italy. They developed a Ku band configuration that's based on a robust design that minimizes the impact of mechanical errors on the radio frequency performances. And the layout is based on a self-supporting internal configuration. What does it mean? It means that this component can be built by aligning the guide axis, the filter, with the vertical axis, that is the building direction. For that, all surfaces of internal channels have been tilted downwards. By that, the researchers have achieved quite remarkable performances in terms of parameters for 6 prototypes. All examples now demonstrate a basic point when trying to develop wave or more in general microwave components by selective laser melting. When that, in order to get the best of the technology and somehow accomplished with some issues that are accuracy and roughness, the design has to be conceived, customized, and realized by laser melting. And this is true for any additive manufacturing technology. So this ends my presentation, and thank you for your attention. And I let the next speaker, Peverini Martin Iglesias, to speak.